So having written down the equations of motion, let's now look at the fixed points. Let's figure out where they are and examine their stability. So for easy reference, in the next few slides, I've written down the equations of motion so we'll always see what they look like. Well, there's one trivial fixed point, which is the extinction fixed point, and that's where all the densities are zero. If we just look at the equations of motion, if we look close to 0, 0, 0, all the nonlinear terms are higher order and can be neglected, and then the equations reduce to n1 dot is equal to n1, n2 dot is n2, n3 dot is equal to n3. These grow exponentially with n. So if I start anywhere except right at the origin, I will flow exponentially away. So this fixed point is unstable. The next type of fixed point is where we have just one species surviving. So for example, we could have the fixed point 1, 0, 0. By inspection, it's clear that if I set n2 and n3 equal to 0 and n1 equals to 1, that serves as a fixed point. And in addition to 1, 0, 0, there's plus cyclic permutations. So the fixed point 0, 1, 0 and 0, 0, 1 are also fixed points, one species fixed points. And as we're going to see, whether or not this fixed point is stable depends on the values of the competition parameters alpha and beta. So let's look algebraically a little bit more carefully at the one species fixed point. So let's examine now the stability of one species fixed point, this fixed point 1, 0, 0. So the program is straightforward, as we've seen even in 2 dimensions, is that we write the variables close to the fixed point, plug them into the equations of motion, and linearize about the fixed point. So we'll write our variables n1 is equal to n1 star plus epsilon 1, but n1 star is equal to 1, so 1 plus epsilon 1. And n2 is n2 star plus epsilon 2, but n2 star is 0, so this we'll write as epsilon 2. And n3 is equal to epsilon 3, where the variables epsilon I are intended to be small. And then we substitute into the equations of motion and see what we get. So for the very first equation, n1 dot, and when I take d by dt of n1, n1 star dot is 0, and so I get on the left-hand side epsilon 1 dot. And on the right-hand side, I'll have n1, which is 1 plus epsilon 1, 1 minus n1, but 1 minus n1, as you can see by the definition, is just equal to minus epsilon 1 minus alpha epsilon 2 minus beta epsilon 3.
In the limit where epsilon 1 goes to 0,
then the epsilon 1 correction on the left-hand term gives rise to only nonlinear corrections, and so we can ignore it. And so we have minus epsilon 1 minus alpha epsilon 2 minus beta epsilon 3. Similarly, epsilon 2 dot, following exactly the same line of reasoning, that's equal to epsilon 2, 1 minus beta 1 plus epsilon 1. Because n2 is 0, n3 is 0, only n1 is non-zero. And in the limit where epsilon is small, we keep only the linear terms, and so we're going to have epsilon 2, 1 minus beta. And similarly for epsilon 3 dot, we'll have epsilon 3, 1 minus alpha 1 plus epsilon 1. And so this goes to epsilon 3, 1 minus alpha. So we can write our matrix equation, our linearized matrix equation, epsilon dot is equal to the following matrix, minus 1 minus alpha minus beta, 0, 1 minus beta, 0, 0, 0, 1 minus alpha times epsilon. And the eigenvalues of this matrix are equal to minus 1, 1 minus alpha, and 1 minus beta. So the point that we learn from this is that this fixed point is stable if all the eigenvalues are negative. And they're all negative if alpha and beta are both larger than 1. On the other hand, if either alpha is less than 1 or beta is less than 1, or they're both less than 1, then we'll have one stable direction given by the eigenvalue minus 1 and either one or two stable directions. So we have a saddle point if at least one of alpha or beta is less than 1.
So now we've understood the stability of the one species fixed point.
Let's look at the stability where there's two species fixed point and their stability. So to be concrete, let's assume that the two species fixed point is that n1 and n2 are both non-zero, but n3 is equal to 0. So I'll assume that the fixed point value of n3 is equal to 0. So to figure out what are the values of the fixed points, we just have to set n1 dot and n2 dot equals to 0. And so setting n1 dot equals 0 gives the condition that 1 minus n1 minus alpha n2 is equal to 0. And setting n2 dot equals 0 gives us the condition 1 minus n2 minus beta n1 equals 0. And if we solve these two equations, we will find that n1 star is equal to 1 minus alpha over 1 minus alpha beta, and n2 star is equal to 1 minus beta over 1 minus alpha beta. So these are the fixed point values. And then to look at the stability, again, we'll do a linearized analysis about the fixed point. So we write again, n1 is equal to n1 star plus epsilon 1, and n2 is equal to n2 star plus epsilon 2. And in this case, we again will have an equation of motion, linearized equation of motion, that epsilon vector dot is equal to the Jacobian matrix times epsilon. And here the Jacobian matrix is the following, and it's just a matter of straightforward algebra to show this. It's equal to minus 1 minus alpha, 1 minus alpha, minus beta 1 minus alpha, minus beta 1 minus beta, minus 1 minus beta, minus alpha 1 minus beta, 0, 0, 1 minus alpha beta. So 1 minus alpha minus beta, 1 minus beta. And then all divided by 1 over 1 minus alpha beta. And the eigenvalues of this matrix are the following. Lambda is equal to 0. There's another eigenvalue, alpha plus beta minus 2 alpha beta over 1 minus alpha beta. And finally, 1 minus alpha plus beta 1 minus beta divided by 1 minus alpha beta. Now we've analyzed what happens at the two species fixed point, and then we can go back and say that we found our two species fixed points. They're like n1 star, n2 star, 0, plus cyclic permutations. And in general, these two species fixed points are unstable. I'm not saying much more about these because this is not the interesting situation of the system. So let's look at the three species fixed point and its stability. By symmetry, we expect that the three species fixed point will be symmetrical it'll be a symmetric fixed point. So let's assume that all the densities are equal, and then we can use any one equation. So if we set n1 dot equals 0, we'll get 0 is equal to 1 minus n minus alpha n minus beta n. I'm assuming the fixed point is non-zero so that we can forget about the n prefix. And from this, we get that n star is equal to 1 over 1 plus alpha plus beta. So we see that when all three species are present, their densities are less than 1. They're less than 1 because of this competition parameterized by these two parameters, alpha and beta. As alpha and beta increase, then the density of the three competing species are reduced because of the competition. And once again, now we look at stability. And so we again write n1 is equal to n1 star plus epsilon 1, n2 is equal to n2 star plus epsilon 2, n3 is equal to n3 star plus epsilon 3. And so we end up with the equation of motion epsilon dot is equal to the Jacobian times epsilon. We are here, the Jacobian matrix is much simpler in form because we have a symmetrical situation, and it's minus 1 minus alpha minus beta, minus beta minus 1 minus alpha, minus beta minus 1. And the eigenvalues of this matrix are equal to the following. There is an eigenvalue minus 1 plus alpha plus beta. And then there are two complex conjugate eigenvalues of the form minus 1 plus alpha plus beta over 2 plus or minus I root 3 over 2 alpha minus beta. So here something rather interesting arises because we see that if alpha plus beta is less than 2, then the real part of lambda is negative. So that means that we'll have stability, or alpha plus beta over 2 less than 1. Because this implies that the real part of all the eigenvalues are negative. Now we have characterized most of the behavior or most of the stability behavior of the three species fixed point. So the three species fixed point is 1, 1, 1 divided by 1 plus alpha plus beta. And this is stable for alpha plus beta less than 2. So these types of fixed points are what might be called the dynamically dull fixed points, because they're either simply stable or saddle points, but they mirror what we've seen in 2 dimensions. But now there's something new happening in the 3-dimensional system. It turns out that if alpha plus beta are greater than or equal to 2, and we also need an additional condition, either alpha is less than 1 or beta is less than 1, there is no stable fixed point. So this is a new type of behavior that is a feature of greater than 2-dimensional competition models of this kind. And now we want to examine what is going on when the system is not attracted to any stable fixed point. Where does the flow end up? Does it just wander around forever? What's going on? So this is our goal now, is to try and understand this dynamical behavior.